Hello, welcome everybody. We're going to give people another minute or so to get logged in, and then we will get started. Give people one more minute to get logged in, and then we're going to get started. Why don't we get started? I want to welcome everybody to our fifth of six sessions on reducing the risk for child maltreatment and treating its consequences, our national training series on the application of causal science. Today is our fifth session. We're really going to focus a bit on the more sciencey part of the science. So we're going to focus on advancing predictive and causal science for, wow, I can't speak today. Advancing predictive and causal science for child maltreatment. We're really excited to have everybody here today. If you can go to the next slide, Glenn, real quick. Just a couple housekeeping things as we always do. The slides will be available after the webinar. We're also recording the webinar and we'll send that out to everybody who registered. By all means, feel free to share that recording with others who you would find it interesting, who you think would find it interesting. Today, as I mentioned on the tops at the beginning, in the last couple sessions, we've focused a lot on kind of application of causal science to child maltreatment on the intervention side. And today we're really going to talk about some of the basics on the science side. Um, Feel free to jump in with questions in the chat or raise your hand. If you throw them in the chat while Glenn is doing the presentation, we'll either bring them up at a convenient time to pause or bring them up at the end, depending. But the goal today is really to have a really thoughtful and robust discussion of some of the science behind causal data science. So next slide, please. This is our executive team associated with the CHAMP Center. And we will go on from here. Slide. There we go. So I think with this, I'm going to pass on to Glenn. He's going to start with a little bit, if you're new to this, a little bit of an orientation of what we've done up until now, and then dive into the meat of the presentation. So with that, I will pass it on to Dr. Glenn Sachs.
Hey, thanks, Andy. So welcome back, everyone. We're really glad you're here. And we're going to kind of dive into what is causality, how it is important, and how you understand it through science with methods. And here are some disclosures for me. And now I'm going to review some key concepts just so we're all caught up. People are new to this, so we're reviewing these concepts, but I think they're going to be important for everything. So again, this is something I've shown you in every presentation. It brings everything to the encounter with the kid or family, and it's all about two questions. Is she at risk for a bad outcome, and what can I do to reduce the risk? And the first question is a predictive question. The second question is a causal question. And we make a big mistake confusing the two. And that's fundamental for everything. I've shown you this. Remember, figuring out how you could intervene, as we've repeated as a mantra. If it's green, you can intervene. If it's red, get that out of your head. These are confounded factors that have statistical association in red with the outcome. So they look like they might be promising. They predict the outcome, but they don't cause it. And then intervening on them will not change the outcome. And we then move this into clinical care, which uh, causality is involved with everything we do, because clinically, with kids' families and in practice or anything we do in life, because anytime we take an action, whatever it is, and we're anticipating the result of the action, we're using causal knowledge in our head to do that. We often don't think of it as that. Every time we cross the street, we bet our life on our causal knowledge, right? When we look both ways, all of that. So the take home here is that causality is fundamental for everything, our care of kids and families, and everything we do in life as we act on the world. It's all about prediction under conditions of intervention. So last time we reviewed the sorry state of our science, um, because there's all kinds of information. We have largely predictive information about correlates with outcomes, but our science doesn't distinguish what's predictive and what's causal, and that's a central problem. And then we talked about scaling the translational wall, and we need causal methods to do that. And so we talked about last time, two fundamental conditions are required for a finding from our science to find its way into our practice, to scale the wall, so to speak. One, um, the finding must be causal to reveal how to improve outcomes, and to apply this causal finding to a person, they need to be classified by that finding so we could use their data to know whether they fit into a category of risk and probable response to an intervention. So these are all very fundamental. We spent a lot of time with this last time, and simply, what a statement of what I might call the medical causal paradigm. When individuals are diagnostically classified by cause, their clinical data can be used to estimate their likely response to an intervention targeting that cause. When the intervention is given to these individuals, their prognosis likely improves. So, fundamental, simply true in every area of medicine, in mental health, in related to maltreatment, simply true. So, how can we bring our knowledge to this? And so we talked about the medical causal paradigm being a learning system where we're continually learning and testing in the way we talked about. I won't go through this in detail. Today, what we're going to focus on is what people think about as very elusive, is discovering causes through our science, because everything follows there. We can't think of diagnostic classification that's going to matter without it being based on a cause. And we can't think of an intervention improving an outcome unless it targets a cause. And these things, this moves together to, over time, make our knowledge and tools better and better and better and better. And this just describes how fundamental this is. And so, because we're going to dive into causal methods today, just back to definitions. I've shown you this like many times so far. but the difference between predictive and causal knowledge, where you look at two factors, A and B, factor A predicts B if knowledge of the value of A informs knowledge of the value of B, and in our conventional methods, we are able to infer this all the time. However, that's way different than causal knowledge, because factor A is causal of B if factor B is dependent on the value of A. And so this has huge implications for intervention, because if there's a dependency, then if we intervene and change the value, we would expect the value of B to change. And it's impossible for an intervention to result in a change if it's not causal. And we've talked about how A could predict B without being causal. I've talked about, the example with yellow fingers and lung cancer. They're highly correlated, but there is a common cause related to smoking. Okay, to today's session. So we're going to review principles of causal science. I'm going to introduce methods at a very high level, because most of us in the room, participants, haven't really been trained or introduced much to these methods. So I'm going to use at a very high level, where I'm really excited. We have Konstantin Alferis in the room today, who, is, a world expert on these methods, and so he could elaborate or tell you how I got them wrong, or whatever. But his methods and algorithms are probably the most foremost in terms of taking these methods to medicine and health sciences. And then I'm going to show an example of one of our studies to illustrate the points. And here's some background reading. I've talked with you about our manifesto, which is on the left. Mental health progress requires causal diagnostic nosology and scalable causal discovery. We've sent that around. There's also a chapter in Konstantin's book, written by two of the three authors are faculty, Eric Cummerfield and C.C. Ma. And if we haven't already sent that around, we'll send that around, because it's a good background as well. And of course, Konstantin's book is your perfect source for all of it. Okay, so today we're going to focus on causal discovery. So let's just talk about first principles. So principle one, there's a causal process that generates the data that is used in scientific research. So if you look at this is called a causal graph, which models a process generating the data. But let's be grounded in this, because let's call the process that generates the data the truth, and the scientific pursuit is to approximate that truth. Oops. Okay. As I just said, scientific research concerns the discovery of this process regarding an outcome of interest. So if you look at O, that's our outcome of interest. And so our pursuit is figuring this out, determining it in a rigorous way with a valid model. And so that causal process ensures that any effect of any cause of an outcome of interest will be statistically associated with it. So if you see here, and we've talked about this before, of that, if that model I just showed you perfectly approximated the process, then you could see that any of the effects will be statistically associated, and that will trick us into believing, if we don't really understand this, that these may be intervention targets, when you could intervene on anyone for 1,000 years and it won't change the the outcome. So, variable 2, for example, is causal on the chain to the outcome. We would expect that intervening on it will change the outcome. However, 17, which is an effect of 2, is confounded by 2 if you see the common cause between 2 causes 17 and 2 causes the outcome along a chain. It's confounded. We would expect this would correlate, maybe very significantly. And this would be replicated because confounding should be expected to replicate. So again, we have to be careful about this variable 17s. And so, what I've done here is just, put these are confounding. Look at all this confounding from these variables that we have to be very careful about if we don't understand the process that generates the data. And so a scientific study of the effect of any variable on an outcome of interest has to be guided by the process that generates data about that outcome. So here is the process. So when you conduct a study, let's say you have a hypothesis about 2 in the outcome or 17 and the outcome. So you maybe you don't know the process before. You should know. I mean, if we advance causal science here over time, we're going to know more and more about the process. Right now, we don't have a lot of knowledge about this. So we'll collect data. So let's just in this hypothetical study say these data on these variables were collected, and you have a hypothesis maybe that 2 is causal of the outcome or 17 is causal of the outcome. What's going to guide you? You have 12 variables measured. 1 is the outcome, 4 are the causes, 6 are confounded. 1 is an effect of the outcome, and you have 6 causes that are hidden. So you have to think about this because this is how we conduct our studies, right? So this is the information we have. So as I just said, let's say you have these hypotheses guiding your research, and you have mainly correlations between, because all of these will significantly correlate with the outcome, as I've said before. So how would you test these hypotheses? And again, the process generating data entails all causes, each of their effects, and the outcome's effects will be statistically associated with the outcome. That's guaranteed, given what we know about causality and processes generating data. So our job here is, with knowledge we have, how to distinguish which are confounded, which are causal, how to discover, how to approximate the causal process generating the data, how do we model it well? And so again, how would you test these hypotheses? So we pick strategies to model and to test hypotheses, whatever, but they're rigorous to the degree they're capable of distinguishing cause of the outcome from their confounded effects and the outcomes effects. So we have conventional methods. I want to go through them because we have this incredible confidence that randomized controlled studies are the way of knowing the quote unquote truth. And we'll talk about like the advantages, but also the significant disadvantage of these studies. And it's also true that, we could spend days talking about the relative advantages of randomized controlled studies, but it's kind of not such a relevant discussion because we can hardly do these studies. If you look in the literature on risk and protective factors on any maltreatment outcome or any outcome related to mental health, it's very hard, impractical, sometimes unethical to manipulate variables. So we are largely stuck with observational studies, and our literature is full of them. Most of our knowledge about, you know, factors related to outcomes come from observational studies. So, this is a complex slide, but I just kind of let's focus on what's going on with the randomized study. So, on each side is kind of a hypothesis. So, a hypothesis on the left side is manipulating variable 2. Remember, that's your hypothesis will have significant effect on outcome. In other words, 2 is causal of the outcome. So that diagram, 2 goes to the outcome is causal diagram. So then we sample, right? And we randomize into 2 groups, and we want 2 to be in both groups. So that's our criteria there. And our randomization, we're assuming all the possible other causes, which will be the confounds, right? Because a confounding factor is by definition a cause of the outcome as well, other than what you're studying. So you randomize and then you intervene. You manipulate 2 in one group and not the other, and you then look at with actually that should say 2. I don't yeah, no, I'm sorry. You look at the outcome in both groups, and if you look at the causal model that we have right there, you know 2 is causal, so you would expect the outcomes would be greater. Now, what gives us so much confidence? Well, we've managed confounding both by randomization, because it's the causes are assumed to be equally distributed between the groups, and the manipulation by setting the value of 2, we render kind of all of its antecedents, like 3, conditionally independent of the outcome. We also render its effects conditionally independent of the outcome. So, you know, in the example of 17 on the right, so when we do this, we of course don't know it's confounded, and that's the problem here. So we do a randomized study of 17 in the same way we manipulate 17, and actually that the outcome should not be expected to be greater. Basically, if it's confounded, it won't be greater. That's a mistake on the slide. And so again, it's confounding. So randomized studies can enable confident causal inference randomization. However, there are very, very, very significant problems here. One, we can hardly do experiments. And then for outcomes with more than a trivial amount of causes, like just about everything we might study, it's hard to use randomized controlled studies to elucidate the complexity of the process that generates the data. We have to kind of tease it apart one study at a time. It could take decades really. So we need to look for alternatives. So let's go to alternatives and talk about the problem here. So we have our truth, we have what we measured, we have what we know, we have our hypotheses, but here we're going to need to be thinking about and so what you need to know is this, right? It's the process, the causal processes right here. And so, and what's confounded and what's not confounded to make sense of this. So how do we determine that 2's effect is unconfounded and 17's effect is confounded. What we usually do is to either do some statistical control or we match between groups, a hypothesis confounder, but you know, you would have to know before you did the study that 2 is the confounder for 17 or any of these others. Like, let's say you did the study of 20. Well, you'd have to, before the study, it to be designed that you'd need to condition on 7. How would you know that? What we do when we match or statistically control is we do the usual suspect variables, age, SES, gender, sex, that sort of thing. But why? I'd say matching in most studies involves these 3 sort of variables, but you could see why would you expect in every study these would be causal and these would happen to be the confounds for the hypothesized factor. So the bottom line here is we need alternatives. We're stuck with observational studies. There's no alternative really. So how do we infer causes most rigorously? That's really the challenge for the field and what I'll be talking about at, again, a very high level. Let me just, maybe I could stop to see if anyone has any questions about what I've talked about so far.
And you can throw questions in the chat or feel free to raise your hand.
Okay, I'm guessing you want more. So let's keep going. So the discovery of the causal process generating the data concerning a particular outcome is based on determining the conditional independencies in the data for that outcome. So what's called the causal Markov condition is it's guaranteed under certain assumptions, which I'll talk about, that this allows us to tease apart causality. So, it works in these ABC models here that if you're conditioning on B, you're going to take the observed association between A and C. A is going to be independent of C. Or if you condition on B or intervene on either of them, then you're going to make A conditionally independent of C. Now, what I'll be talking about in a few minutes is this miraculous concept called the Markov boundary, which is the direct causes. Direct means unmediated causes, the direct effects, and the direct causes of the direct effects. This is all the non-redundant information you can find in data. Basically, if you know the variables in the Markov boundary, you don't really need to know information about other variables. You know, mainly if your studies are done really well, all of that's the assumption, and that's a key concept for what we do with the causal methods. Again, I'm going to talk about the assumptions required for this because our confident inferences are based on certain assumptions. So, the definition, rigorous application of computational methods to observational data in order to discover intervention targets that can change outcomes. So we have, people who've won Turing prizes, Nobel prizes. The recent 2021 Nobel Prize isn't with our methods, it's with natural experiments, but there are, there is a great deal of scientific interest in these methods and a lot of a lot of rigor to these methods if people are worried about this being new and not tested and that sort of thing. And we could add to this group. I mean, Konstantin, who's in the room, created the algorithms, um, you know, based on some of Judea Pearl's early work and others that are really make some of this tractable, make it efficient computationally, and especially as applied to health problems. So just, some qualifications here. How do the methods work? They're highly technical and really hard to do justice in time in this presentation. So they apply algorithms that are mathematically proven to find the conditional independencies in the data. I'm going to talk more about that. So what does this mean? That given a particular outcome, what is the set of variables that would render all other variables independent of it? That is to say, its Markov boundary. And this approach powerfully addresses confounding because confounded factors are rendered conditionally independent of the outcome given its direct causes, which we could discover. And they're discovered, causal models with the standard here. What we're aiming for, of course, is to model the causal process that generated the data, to approximate that as best we can. That's the goal. And it's the goal of all scientific research related to causality is to best approximate the causal process generating the data. Okay, so this is, a caveat here is this is not like, it's not a linear thing. I'm going to describe it that in this way because it's easier to understand, but the data scientists who do this, it's not linear in this way, but I think this is a good way to understand what we start with. So you look at all variables here, as we've done with the model I've just showed you about, and the first question is the correlate of the outcome. Is it statistically associated? Yes. Okay, it's a potential cause. No, let's discard it because we know it's not a causal factor. Okay, now we deviate from convention, at least in maltreatment and mental health, by beginning with different causal methods. The first are structural causal modeling methods, which really look at how causal factors fit together. They start with the Markov boundary of the outcome and based on its direct causes, build Markov boundaries of each and working their way up to model the processes. That's local to global learning, where you're starting again locally right around the outcome, and then you're building this global model. Okay, so this tells you also when you do this, because of conditional independencies, that you now could distinguish from measured variables anything that was confounded and rule it out. So if you find when you do the conditional independency tests required for structural causal modeling, if it's unconfounded there, it's a potential cause. But if it is confounded, it it isn't, and I'll call it a causal pretender, because you'll see its replicated statistical association and get excited about that. But again, it's confounded. But then why do I call something unconfounded a potential cause and not a cause? Why am I not jumping up and down right now? Well, because these methods could look at thousands of variables that are measured, but there's latent confounding. there's always the possibility of variables unmeasured, but latent confounding methods can be applied that obviously won't tell you what the unmeasured cause is that confounds it, but will say, be careful about this connection between a variable and an outcome that you think is probably be causal, but you've only ruled out confounding for measured variables. So latent confounding will say there's a signature here that it's probably confounded by an unmeasured variable. So then we take out causal pretenders there. And if it's unconfounded by a latent variable, then we may be excited about it, but not yet, because we have to estimate its effect. You know, if you look at like the model I showed you, we'd expect, variables many steps up from the target are probably going to have a weak effect, maybe hardly noticeable at all. So we don't want to, even if it's causal, we don't want to say it's an intervention target unless we estimate the effect. And we do this, as I'll be talking about, with do calculus. And what do calculus by Judea Pearl, he came up with this idea. And the essence of it is that the effect you might estimate is guaranteed to be unbiased if you know you've ruled out all the causes, measured or unmeasured. So you do this, and then you find causes will vary on the effect size, which means essentially if I change this factor, this causal factor by 1 unit, what is the change I would expect in my outcome? And that has huge, huge, huge implications for intervention. So if it has a strong effect, then let's call it an intervention target. And if not, it's not a causal pretender, it's a cause, let's call it a causal weakling. But we then focus on the intervention targets. Um, and again, that's really what it's all about. That first slide I showed you, risk, when we're working with children and families, there's risk, no risk. But then it's how do I reduce that risk? And it requires that I know an intervention target, which is by definition a cause, with a strong enough effect on the outcome to lead to what an expert say would regard as a clinically significant change. So to just say a little bit more about these processes, I mean, essentially, we're mapping the data to the causal process that generated the data. We have data. This gives us joint distributions, and those joint distributions map onto a causal graph, which is, what I keep showing you. And this is an essential principle here about bridging the data to the graph through the joint distribution. And so, you know, different different causal directions, causal models, so to speak, have different signatures that you're able to see. And that's a key part of this. And so, this is a model this Constantine created for me or for other people, whatever, but it's a very useful way of thinking about this, where you vary, what's causal here, what's confounded, which P1 and 2 will call them passengers, what's hidden. What I showed you, remember, and you saw that bigger causal model, which modeled the process generating the data, but only 12 variables were measured, and I think only 4 out of 10 were causes. So there were 6 hidden causes, all of them available if you look at what H2 does, a hidden cause, it's confounding variables here. So, like it confounds P2, but we don't know it because it's hidden. So I've talked about what the causal Markov condition is, and it's true under assumptions, which are usually demonstrated, but even if they're not, there's ways of handling this, as I'll talk about in the study that I'm about to present soon. So the faithfulness condition says the independencies observed through the causal Markov condition are the only independencies to be found in the data. If that's in place, it's guaranteed that your model is correct. So again, if the causal Markov condition and the causal faithfulness condition hold, the graphical model represents the causal structure found in the data. And deseparation it's an important but highly technical concept developed by Judea Pearl, which also is kind of at some level part of the algorithms of conditional independency tests, where you look at two variables and you say they're deseparated related to other variables in one of these graphs. They're called directed causal graphs. If those variables, if they're independent, conditional on Z. So anyway, it's a complex topic. And then here, the Markov boundary is the smallest set of variables pertaining to an outcome that yields maximal predictive accuracy. And this is the direct causes, the direct effects, the direct causes of the direct effects of the outcome. So this is important, and these ideas will guide the study I'm about to tell you about. Konstantin, anything you want to add to this or subtract?
Well, I think it's very important for the audience to really indicate what they know already, what they hear for the first time, what's not clear, and respond to that. There's a ton to say about these concepts. They're very foundational. There are many details, but I would prefer to maybe try to respond to the audience's specific questions.
So any questions right now about this or about anything? Must be something. Anything? So you either completely get it such that it seems almost trivial, or it's a little far for you're struggling with it. So I'm just hoping that people will be able to will ask questions so we could clarify things. Again, it's even though this is actually not very technical, for someone who wasn't trained, this looks very technical, and we get that.
So maybe, Glenn, we need then to say something along the following lines. So everybody who's in healthcare and health sciences takes statistics courses. In statistics courses, they say, oh, Fisher said correlation is not causation. If you want to learn causation, you need to do experiments. And therefore, you do experiments in the lab, you do experiments in clinical trials, and you learn causation. And if you don't do these things, you cannot learn causation. That was true in Fisher's time, maybe 70, 80 years ago. It's definitely not true today. Through the amazing intellectual contributions of many Turing Award and Nobel Award winners, we have now a rich methodological toolkit that allows for the reliable discovery of causal knowledge without doing experiments, mathematically proven to be correct under broad assumptions. I think that's the main message that this audience will benefit by memorizing, keeping with them. Now, the exact details of what are the algorithms, what are the assumptions, how they operate, example cases where they have been tested, benchmarked, applied in real life, I think this is a very big and interesting discussion. But as of now, I think this is the main concept: is that causation can be discovered without experiments. In many cases, we have to learn causation without experiments. Why? Because experiments may be unethical, may be infeasible, may be too costly, maybe take too much time, and certainly manipulate one variable at a time. We cannot learn complex causal systems such as the ones involved in mental health and socio-biological and medical situations. Why? Because there are mathematical theorems that say that to learn complex causal system structure, you need to manipulate up to all variables in the system simultaneously, and that cannot be done like in this universe. Okay, so that's why we absolutely need to blend, incorporate, and integrate all available tools, including experiments and non-experimental causal algorithms, in order to discover the best possible causal picture of reality that we can.
Yeah, I mean, go ahead, Andy. You're about to say something, or someone? I'll just say that, when I think of this and the necessity of knowing a cause to know how to intervene, it's like, what's the alternative? What can we do except something like this? And, if you look at, I reviewed like the problem, controlling variables, knowing about confounding with, the methods we conventionally use, um, and so it's like, if it's not this, what is it? Okay, I mentioned this before. Estimates of the effect of factors on outcome are unbiased if confounding is excluded. So this is really important because it's what it's all about. Like, okay, if I tell you a causal model said this variable was a cause, and you were thinking of, and you had an intervention for it, your next question is, okay, it's causal, great, but what should I expect the result of an intervention to be given the cause? Is it a large effect? Is it a small effect? Is the effect, whatever its size, would it be clinically significant? So this is really, really key because everything moves here to be clinically relevant. And so, as I mentioned before, a lot of this is based on the do calculus because unbiased estimates happen when we have rigorously excluded confounding. And so, here is a model where, with one exception, confounding is excluded. And this is the exception. There's some confounding here if people see that. And essentially, to look at effects, there are two pathways to the outcome here, as you could see, 2 to 1 to the outcome and 2, 1, 4 to the outcome. And so we're estimating effects based on the pathways that are seen, but then and mathematically, it isn't a subtraction to the degree I understand it, but you're also reducing the size of the effect given any confounding pathways too. And so, here's 1, 5 to 1, 5 to 4 contributes to the pathway of 2, 1, 4, 0. Okay, so there's a growing literature, certainly outside of our field in healthcare and many other areas, economics especially, in kind of mental health and maltreatment, and this was written in like 23. There's several new studies, that sort of thing. It's kind of growing. A bunch of these are our group because we're one of the only labs in the field focused on these methods. It's also true that, applying it to mental health and maltreatment, etc., it's still relatively new, and we're certainly learning all the time about it. And so here are some studies published, empirical studies published. We've focused on PTSD, especially, but not only that. And, we found causes and causal effects here. So I want to talk about a study we're spending a lot of time on now. It's unpublished. It's gives you a sense of how this could work. So basically, this is using causal data science for looking at predicting maltreatment exposure and then determining intervention targets. And this is from the Fragile Family Study, which I expect many people here know about. So it's started with a sample of pregnant women from hospitals across the United States. The initial cohort had almost 5,000 subjects. They were they weighted them in high-risk families, especially single mothers, but not only at the time of entry, and then baseline interviews right after birth, and then follow up over time. And so this contains a huge range of developmental, environmental, biobehavioral risk for lots of different outcomes. So we looked at these waves, and our target outcome variable is maltreatment at the 9-year-old data collection, which is between the age of 5 and 9. And this is how we defined it. And so, again, we're looking, did the child, were they exposed to maltreatment in this period of time? So it's based on this number of children and over 1,600 variables. It's a lot. And so what we found is that 9% were exposed and 91% were not. So the first thing we have to do in prediction is, what's a model that might distinguish the 9% of kids from the 91%? And one of the things is that the variables, actually not in the predictive model, in the causal model, were all from age 5 and younger. But let's talk about prediction first. And so, we're looking at what's the most accurate predictive model that could be found in the data. This is a highly technical term, but it's using state-of-the-art machine learning methods. Now, we want to make sure, like, if we find, let's say, a model with 500 variables, even if it's highly predictive, how are we going to bring 500 variables into the field to look at who might be at risk or not? So we want to drill down, and we use the Markov boundary feature selection to do that. Okay, as I've just said here, we're looking at, is the model we find the only one consistent with the data, or are there multiple other ones? We do this by saying, is there only one Markov boundary or more than one Markov boundary? And these are algorithms we use. And then we're building a regional causal graph, and we're moving from there to get a global model. Now, we haven't implemented number 5 to look at hidden variables. I mean, we're looking at over 1,600 variables to look at confounding, but that is one of the limitations to the study. And then we're estimating causal effects using the do calculus. Okay, so let's look at prediction. How can we find a model that distinguishes the 91% not maltreated from the 9% that were? So we found a predictive model, but it's over 1,200 features. Now, this is amazingly predictive. An AUC of 0.96, you know, AUCs, for those who don't know, vary between 0.5, which means the model is random, to 1, which means the model is perfectly predictive. And it integrates sensitivity, specificity, that sort of thing. So this is amazingly predictive, but do you see me jumping up and down? No, because we can't bring 1268 features into the field. However, there is something that will save us and make me jump up and down. What is it? Who wants to say what it is? Let's see if you're paying attention. What will save this for clinical utility? Shout it out.
If it can be replicated?
Um, no,
You
because
said guess.
yeah,
That was my guess.
so good guess. I'm glad. I'm really glad. But that's not it. One of the things about replication is, again, there's issues about causality, but it's not because this could be replicated. I mean, I'm just thinking of what you said. It's also, we want to be, and we do this by looking at different slices of the data, finding the model that really fits, is true in many slices, and then you could cross-validate in other data sets. So it's a good point, but that's not what I'm looking for, of what's going to make me jump up and down. And I think everyone in this room, when I tell you. Anyone else? Okay. I hear a drum roll in the distance. It's getting louder. So the Markov boundary feature selection saves us. I regard this every time I see it as kind of a miracle.
Glenn, could you talk a little bit about the Markov boundary? Because I feel like it's something that we talk about a lot, but like what that actually is, I think it's lost. I will speak for myself on many of us.
So we're very lucky because we have a world expert on the Markov boundary in the room. So it's, yeah, a little bit like in the movie Annie Hall when Marshall McLuhan was standing in the line. So Marshall or Konstantin, why don't you talk about what the Markov boundary is and why it's
Sure.
important?
So the Markov boundary is a set of variables. So if you think about a data set that has various observations across many variables, is this set of variables that has a very specific property. The property is that it contains all the information in the data about a third response variable we're interested in predicting or diagnosing or prognosing. And at the same time, it has no redundant elements. So in other words, you cannot take out anything from the Markov boundary without reducing the predictivity for the response variable of interest. So it's the most predictive set for the response. That's also the most parsimonious set. Every other variable in the set may or may not have information about the response variable. If it doesn't have information, it's irrelevant. If it does have information, it doesn't add anything to the Markov boundary, it can be discarded because the Markov boundary has that information and more. And finally, the Markov boundary has also causal interpretation under assumptions and other conditions. So if we don't have latent variables, hidden variables in the data, for example, and if a very broad distributional family of a family of distributions describes this data set, which are called faithful distributions, then the Markov boundary is the set of direct causes, direct effects of the response, plus the direct causes of the direct effects, so-called spouse variables. And if the response variable is a terminal variable, like death or some terminal, diagnosis, there is nothing out, subsequent to that, then the Markov boundary is only the set of direct causes. So you see, so the Markov boundary has both, it's a set, theoretic notion, and has both predictive and causal implications. And the good news is that starting from 2002, we have algorithms that can learn the Markov boundaries correctly, very, very fast, with very small sample sizes, and scalable to, as of now, to hundreds of thousands or millions of variables. So they are, utterly scalable to meet the demands of any kind of health or biomedical data set. Does that answer the question, Glenn?
For sure. Yeah. So I have a fun game we can play right now. I know everyone wants to play a game. We've gone from 1,268 variables to 15. Put in the chat what you think the reduction in the AUC is by reducing variables to that. So now we're going to predict the outcome of maltreatment exposure from 15 variables, not 1,268. So just, every answer is okay. I want just put a number in there. 0.88, 0.85. Yeah, I mean it's reduced, but it's still high. Other people, no reduction. Okay. An ambitious guess, Andy. Okay. Let's two more people. I know you're in deep suspense. Come on, just put a number. Okay. Okay. 0.77. I always can count on Iris to step in. Okay, great. 0.77. Anyone else? Okay. I will take everyone out of their misery because I know how excited you are. 0.96. So just think of the meaning of this, put this together with what Konstantin said. You reduce the number of variables from 1268 to 15, and you don't diminish the astonishingly high predictivity of the model. And it's because, again, mathematically, if you know what's in the Markov boundary, everything else doesn't really matter regarding prediction. So this is, and I would say, and we've done many studies now, this has always been true. It totally blew me away the first time I saw it.
So, Glenn, can I add one little thing there?
Yeah.
So, I think the most striking thing is not that you can reduce 1,268 to 15. Of course, this is a 100-fold, two order of magnitude reduction is extremely impressive. But once you know the Markov boundary, and the Markov boundary typically in real life situations is very small, okay? There can be infinite variables, okay? All variables mathematically definable in the universe that do not matter. So it's not just 1,000 or 10,000 or 100,000. It's infinite. Nothing else matters. You know this set of variables, that's it. You have described the response as well as possible. So to me, that's more a little bit more impressive than, but you are so right. In practical real life analysis, depending on how many variables we start from, and for example, if you have molecular or genetic data sets that have tens of thousands, hundreds of thousands of variables, a 1,000-fold reduction is absolutely common. Nothing, strange about it.
Yeah. Okay, and now let's talk about the causal modeling. So, well, first of all, the other thing is the model the only one consistent with the data? And we did find multiple Markov boundaries. Now, we've seen this before several times. And so at the one level, you could get very discouraged because this violates the faithfulness assumption because, there's more than one conditional independency in the data by definition here. However, what we found out is you could use the multiple Markov boundaries to quantify your level of uncertainty. So basically you'll find, and as I'll show you, many variables that are in every one of the Markov boundaries, so you could be very, very certain about those variables. Some variables may be in half of the Markov boundaries, so that reduces your uncertainty, uh, all of that. And it's complex, but we've used this to look at, like when we estimate effects, we could look at the range of effects given this, and if we have variables in all of the boundaries, then there's one effect that we could see. Okay, so we build a rigorous, so basically between the direct causes and the indirect causes, which are mediated by the direct causes, we have about 40 within 2 steps of the outcome. And then we estimate causal effects. So this is complicated, and it just, so I don't want to get lost in this, but I'm listing the 40 causes. I'm listing, if you look at the table on the left, the timing when it was measured. Remember the fragile families, like we have before birth, we have lots of it. Where we got, what person this was relevant for, father, mother, or family. And this is kind of prenatal variables. So you could see like average total effect, min to max. So that's it's kind of a range within boundaries. And then, what we kind of say is, is this in all the boundaries, all the Markov boundaries? So then we could look at p-values that they're 100% significant, like all of them in all the Markov boundaries. So you could see prenatal smoking, but then alcohol, this variable is only in 33%. So I'm going to summarize things that are important later. What we're also, you could look at what the variable is, like who it's from, the main concept, and the effect size, the odds ratio, and the range of effects given the Markov boundaries and what it falls in. Also, right after the blue is we kind of we're looking to bring this into the field. And so we're looking at kind of the frequency to expect these causes actually in the child welfare prevention group. And let's see. Yeah, so you look all subjects in fragile families, subjects contacted by CPS, and subjects monitored by CPS. So we're looking at the causes and how common they are in the population. I want you to, we've kind of selected variables in the green to focus on, like child experienced family violence during wave 3. That's year 1 to 3. So it's not a bad effect size. It's in 100% of Markov boundaries. And it's kind of with other variables, we have family violence becomes frequent. And so, again, I know this is a lot, but we're looking at lots of potential causes. And it's in our next and last session, it's how do you use this model to go into the field to change decision making in the field regarding kids and families. That's what we'll talk about next. But we start by a model here and all this information, which I'll go over a lot next time, about the different causes. We're looking for the causes with a large enough effect that are frequent enough in the population, could be measured in typical settings, and have interventions known to change them. And of course, we need to define the interventions and look at what the literature says about their potency, etc. But we start with this. I'm just there's like, what, 40 causes along different people. I'm going to show you a slide that picks what we say is most important right here. So basically, there were, if you look under description, these are, I think it's 15 causes, each of them within two steps. It's either a direct cause or a one step from the direct cause, an indirect cause. So if you look at description, that's the variable. The odds ratio, it gives you, what the odds ratio, and everything. For people who don't know about odds ratio, everything 1 and above is kind of risk. Everything below that is protective. And so basically what we've done, and I'll talk a lot about this next time, is organize these causes, which we thought could be intervened on, in 6 different groups. Each group, if you think about it and you look at the different causes, has kind of a singular intervention you might think about. Again, we'll talk more. What I have intervention is just right now we're in the process of thinking of different interventions. So it's probably not going to be these interventions, but this is all meant to build a decision support tool for the field. And the actionable causal groups are exposure to family violence, maternal negative attributions of the child's behavior, exposure of the child to corporal punishment from either the mother or the father's vocational disability from a physical or a mental condition, and 5 is either mother or father's anxiety or depression, and then 6 is mother's substance abuse. So this again, out of the 1,600 plus variables, we landed on 15 that we thought were actionable within 6 different groups. And so there's more to talk about this, but I wanted you to have a taste of how this works. Looking ahead, well, next time is all about, like, the models don't matter if you simply publish them, and they don't work in the field. That's when it matters. But to change things in the field, you need an accurate model and then translate that into something that's going to work. I'll also say that we have a group of stakeholders. Some of them are in the room. I saw, Len Bickman's in the room, is on the translation team, where we have data scientists, clinical scientists, clinicians, practitioners of various forms, family members, administrators, policymakers, that sort of thing, looking at the model in order to help us move to a decision support tool that could work in the field. But that's for next time. For now, I think that's about everything I had to say. So why don't we talk about it? And I hope people have questions, comments, arguments, whatever. I'm going to stop sharing my slide. Okay.
So we have one comment, Claire's, and other people should throw their comments in the chat or raise their hand. In the example you just showed, the causal groups are connected to each other, and treating some could probably affect others, e.g. treat mental health. The parents probably affect substance use. Can the data support this logic, or is it more of an interpretation?
No, thank you, Claire. That's an amazing question, and is something I didn't show you as we're putting everything together. But what you're talking about is called a structural causal model. So if you have a set of causes, how do they fit together? Like I showed you, the models I showed you are hypothetical examples of how they fit together. We're working right now on the best visualization of this, but we absolutely need to know it. And that's based on kind of knitting the model together through the Markov boundary as we go locally around the outcome and then move it up so we could really see how things fit together. Great question.
Can I also add something, Glenn?
Yeah.
So it's entirely possible that the various local causes there in the Markov boundary, they do not interact with one another. In these cases, it's a very simple situation. We can estimate the effects of manipulating some of these variables while letting the other ones vary naturally. And we can see what will be the estimated impact on these interventions. If they interact with one another, there's a couple of things that can be done. One of them is to control analytically in the model everything constant while estimating the effect of each variable. And then also we can calculate what will be the effects on the desired outcome variable if we manipulate any subset of variables, allowing the rest to be influenced by them as they may by the causal structure that's in effect. So all of these can be derived from the model, and the proper interventions can be selected and their effects can be estimated.
Yep. Other questions, comments? Andy, or no?
Yeah, so others should jump in with questions. I have one question just to highlight, because you touched on this a little bit, but how do you address the fact that some of the causes may not be in the data set, that there may be things that weren't measured that might have a big impact on the outcome that you just have no idea because they weren't measured to begin with?
Yeah. Konstantin, or is Eric,
Yeah.
who's quite an expert in this, but yeah.
So let me start, and then Eric I'm sure can add a lot of very useful information. So if the variables the model identifies that they are causal and they're not confounded by unmeasured variables, and the estimated effect is very high, then you know for a fact that by adding more variables, you're not going to add much to your desired outcome from the intervention. Now, if they are causal, they're not confounded, and the signal is small, the aggregate effect is small, then you need to add more intervention targets, more variables that are causal in order to bring this aggregate causal effect up. Finally, if there are unmeasured variables and they confound your local causal model, there are algorithms that, very surprisingly, but there exist, that can detect the existence of these latent variables, and in some cases, they can also we can estimate what's the effect of the unmeasured variables. And Eric Kammerfeld is a faculty here at the University of Minnesota who is a world-class expert in exactly how this can be done. So Eric, can you explain more, please?
I don't think Eric is
Yeah,
on.
Sorry, I thought Eric was here. So
it was just
essentially
on my part.
No, it's okay. I should have looked carefully. So here's the situation. All right. So there exist algorithms that have been identified as early in the 1980s. Okay, these are not very new, that detect signatures of conditional independence and dependence in the data that are diagnostic for the existence of unmeasured confounders. And therefore, these algorithms can tell us whether a particular causal edge in the model is decidedly unconfounded by any unmeasured variables, or whether it's decidedly confounded by unmeasured variables, or whether we cannot tell, because nobody can tell. It's not a decidable problem from a statistical basis without experiments. By applying these algorithms, we can separate the identified causes in these categories, and we can decide what are the reliable intervention targets.
Got it.
Okay, other questions? I see Chris Lane in the room. Chris, I don't think I've ever been in a presentation given by me or anyone else where you didn't have a comment, an insightful comment or question.
Well,
okay, they pulled you out of the darkness.
what a lovely thing to say. You have to excuse me. I was having a meeting in our dean's office, so I had to step out in the middle of our meeting. Otherwise, I would have been throwing out jaunty comments much earlier. I just wanted to say that I really enjoyed seeing the table itself with the odds likelihood, for instance, and the treatment protocol. Just in terms of my own training clinic, I actually teach people to be able to identify specific foci in the environment. It could be within the individual, within the family, community, et cetera, and then lay out an intervention objective and then propose practice elements and then monitoring metrics by which to monitor the ongoing effects of the intervention. So all that can be built out, I think, in a way where we're not only building a causal model, but we can start to embed that within a clinical training setting. We're now teaching people to not just think about treatment protocols as monoliths, like I'm going to throw this whole protocol, but to unpack those protocols into intervention objectives and practice elements and monitoring metrics, because you get differential effects, obviously. Not all treatment components in a given treatment protocol exert similar effects. So you have to be able to unpack those in ways with I think, that same sort of level of specificity and precision that you are doing here.
Yeah, no, exactly. And you know, the treatment protocols we usually use were not really formally designed to target causes, but if they happen to have an effect on the outcome, it's because they happen to hit the cause, that sort of thing. And so part of this is to get more formal and specific about that for sure. In our next session, we'll be demoing a decision support tool we've made out of the model I just shared with you. And really what the decision support tool is programmed to do is, given these 6 causal groups, do you have it, yes or no? And then if you assess these 6 causes in the field and input that, then what does that tell you about the child's risk for the maltreatment outcome? What's the level of risk? What are the interventions given the configuration of the 1 to 6 causes? What are the interventions recommended? And what is the estimated reduction of risk from the child and family receiving those interventions? So that's really where we're going, which it sounds like it's very aligned, Chris, with what you're
Very much
doing.
so.
And we'll give a demo of that next week, because
Really look forward to that.
yeah, we're planning clinical trial of that tool.
And I also just want to, I did value also your critique of randomized controlled trials, which I think sometimes are viewed as the ultimate arbiter of truth, oftentimes in the treatment literature. And they're rife, I think, with limitations. Specifically, although they help us to draw causal inferences, they do not lay out causal processes, I think, with the type of precision that we actually need. We need to have something that is much more ecologically rooted, and that maps out onto processes. And so I just feel like the current set of armamentarium that we have for unpacking treatments, that be they randomized controlled trials or unpacking designs, for instance, dismantling studies, oftentimes really do not get us very close to the kind of precision, the verity that I think we're talking about right here, which is a much more dynamic way of mapping out relations between things. What I basically say is, it's just like the Old West. If I want to prevent these people from communicating to that, I cut the telegraph wire. In the same way, we actually want to be able to target either the original costs, or mediating pathways, or both.
No, and so it's all about mechanisms. Can we understand it? Can we get rid of variables that are not mechanistic at all? That's related to the conditional dependencies in the data, to leave us with mechanisms or causal processes understood formally through causal chains. And when you attach an effect size to them in an unbiased way, then you can estimate the results of intervention. And so part of this is really doing our best to bring a formality to this.
Yeah, it's a lovely thing. I also really enjoy conferences where they bring in economists, for example, and sort of econometric thinking, because now that moves us much towards the return on investment, or the bang for your buck that you're talking about right now. If I intervene here, what's the expected reduction in the outcome?
Yep.
And so once again, it's a very synthetic way of thinking that I really appreciate. When I teach these principles, I basically say predictors and causes are both useful for risk identification, for risk screening, but you better have a causal model when you're starting to identify intervention foci and develop, an intervention plan. And many people, frankly, don't know how to do that, when in graduate school, at least.
Yeah, for sure. Thank you. Okay. Other questions? I know you're on the edge of your seat. Don't say we didn't give you opportunities. Any questions at all about this fascinating topic?
And I would just remind folks that we have our closing training series presentation on June. I'm just looking for the date here. On June 10th. So our last one of these in this particular training series will be on June 10th, and then we'll take a break for the summer. Jenna just put the feedback survey in the chat, so please complete the feedback survey, and we will go forward from there. So again,
Yes,
thank you, everybody.
Next time it's bringing these models into the field and how we do that, which I'm really excited about. So thanks everyone for your attention.
All right, thanks everybody.
Thank you. Bye.
Bye.